Welcome to 9.3, the integral test and P-series. So we're going to look at two other ways to prove convergence or divergence of series, and those are the two tests we're going to talk about. So first we're going to start with the integral test. All right, so in order to use the integral test or apply the integral test, we must show f is positively continuous and decreasing. So there's kind of three things there: positive, continuous, and decreasing for x is greater than or equal to 1, all right? And we're going to let the sequence, an, equal the function in terms of n. So we're going to let those guys kind of be the same thing, all right? So then if the series if the integral converges, then so does the series. If the integral diverges, then so does the series. So what we're going to do is we're going to take this series, look at the sequence, all right, and integrate that sequence, okay? So, for instance, if we're looking at our example, the series from n equals 1 to infinity of n times e to the negative n squared, does it converge or diverge? So if we're looking at our graph here, okay, and we're going to let f of x equal our sequence. Instead of n, we're going to replace it with x, okay? So if the integral converges, then so does that series, all right? And obviously, since this is an improper integral, we'll have to set up a limit. But before we can even apply the integral test, all right, we're going to let f of x equal that function. We have to show that it's positive, continuous, and decreasing. So is it positive for x is greater than or equal to 1? Well, you can see that by plugging in values that are greater than or equal to 1, right? When x is positive, greater than or equal to 1, we're always going to get a positive value there. So it is positive. Is it continuous? Well, the domain is all real numbers. There's no value of x for which our denominator doesn't work, is 0, so it is continuous. To prove it's decreasing, we'll take the derivative and show that the derivative is always negative, okay? So f prime, if I rewrite this as x times e to the negative x squared, we can use that product rule. Don't forget the chain rule when we're taking the derivative of e to the negative x squared, all right? And what we can see is e to the negative x squared, that's positive, but this portion, 1 minus 2x squared, that's always going to be negative when x is greater than or equal to 1. Therefore, a positive times a negative, that means it will always be negative. Therefore, f of x is decreasing. So we've gotten those three cases covered. Now we can go ahead and apply the integral test, okay? So if we're taking the integral from 1 to infinity of that function, we can use a u substitution if we let u be negative x squared, du is negative 2x. Since it's an improper integral, we also have to set up that limit as b approaches infinity. All right? So as I mentioned, that u substitution, don't forget to change those limits of integration. And now when we integrate and I substitute it back in, we get negative 1/2 e to the negative x squared from 1 to b. So evaluating this guy here, we get negative 1/2 times the quantity of 1 over e to b squared minus 1 over e. Now we can evaluate this limit as b goes to infinity. We get negative 1/2 times 1 over infinity, which we know is just 0, minus 1 over e, and we get 1 over 2e. So, therefore, the integral converges. So by the integral test, since the integral converges, we know the series converges, okay? And so we would state, by the integral test, this series converges, all right? So one warning we need to discuss, okay, is the integral test limit does not produce the infinite sum value. So this up here doesn't tell us what that sum of the series is, okay? So those are not the same thing. This just tells us that the integral converges, okay? So we don't know what the series converges to, all right? So remember, we need to use the partial sums S sub n and let n approach infinity. So that's how we get what the series converges to. All right, so remember, the last couple of days, we said S is the limit of that series, or the limit as n approaches infinity of S sub n. And remember, S sub n is just the sum of those terms. And so this S sub n is that formula, okay? So the limit of the sum is not the sum, which is a number, okay? So kind of keep that in mind. And again, the integral test, whatever the integral value is, does not mean it's what the series converges to. These next examples are just review from Chapter 8, but they lead into P series, all right, which is our next topic. So let's go ahead and quickly integrate these three examples. Now, these are improper integrals, so we have to set up those limits, right? So if we're looking here and integrating from 1 to infinity of 1 over x dx, we have to set up our limit as b approaches infinity of the integral from 1 to b of 1 over x, or x to the negative 1, and we can integrate that ln of x. Oh, that should say b, not infinity there. Okay, and now when we evaluate it, we get ln of b minus ln of 1. ln of b is infinity, ln of 1 is 0. So we would say that this just diverges. It equals infinity, all right? If we take a look at this next example, right, we walk through this hopefully relatively quickly. Again, integrating from 1 to infinity, this improper integral. We're now taking the limit as b approaches infinity of the integral from 1 to b of x to the negative 2 dx. We can do that, or we can integrate this very nicely, and it becomes negative 1 over x. Evaluating that from 1 to b, we're now taking the limit as b approaches infinity of negative 1 over b plus 1. And when we get negative 1 over infinity, that goes to 0, so we're just left with 1. So we would say it converges. And then finally, when we see our last integral, right, the integral from 1 to infinity of 1 over x cubed dx, setting up our improper integral, the limit as b approaches infinity from 1, or the integral from 1 to b of x to the negative 3, we can integrate that easily. And when we go through, we're going to get 1/2, which converges. Okay, so you can take a look at these three graphs, but this is leading into a P series. So a P series is going to look something like this down here, okay? And we're going to look at this scenario here where P is 1 and kind of talk about that. But let's just use the integral test to see whether this series itself converges or diverges. Okay, and then we'll kind of relate back to those three examples that we just did. So again, a P series is where we would have 1 over n to the p, where n is our value. P is some constant. It's positive and it's a constant. And in this case, we're going to say p doesn't equal 1. All right? So using that integral test, we're going to let f of x be 1 over x to the p, or x to the negative p. For x being greater than or equal to 1, this will always be positive, okay? So let's check. Is this continuous? Again, for x being greater than or equal to 1, yes, this is continuous. Is it decreasing? Well, we have to show that the integral is negative, or sorry, the derivative is negative. So when we take the derivative, negative p times x to the negative p minus 1, we could rewrite this, okay? Remember, p is positive, so if we have the opposite of p, that part's going to be negative. This will always be positive, so negative over a positive will always be negative. So it is positive, it's continuous, and it's decreasing, so now we can apply that integral test, okay? So we're going to integrate from 1 to infinity of x to the negative p dx, all right? We have to change it to the limit as b approaches infinity. And now we can integrate this, and when we do, we get 1 over negative p plus 1 times x to the negative p plus 1. Evaluating this from 1 to b, we get 1 over negative p plus 1 times this quantity. When b approaches infinity, this portion goes to 0, and this portion just goes to minus 1. So when we finally get through it, we get 1 over p minus 1. So it converges so long as p does not equal 1, okay? When p is a positive constant there, all right? So if p doesn't equal 1, we're good to go. So this is leading us into that p series. So let's go ahead and look at the next page and get it down. Okay, so again, a p series is going to look like this, where we have 1 over n to the p, and the terms would look like so, all right? There's kind of 3 scenarios, all right? 1, when p is positive, when p is greater than 1, we converge, okay? It diverges when p is between 0 and 1 inclusive, meaning when p equals 1, it still diverges, but this is a special case. This is called a harmonic p series, all right? So since p equals 1, this is a harmonic p series, and it diverges, all right? So a harmonic sequence, okay, that portion, is going to look like this. 1 over some number in front of n, plus or minus some number. So for instance, it could look like this, 1 over 2n plus 3. That would be a harmonic series, okay? We could call it a harmonic p series, and it would still diverge, okay? All right, some other things to note, okay? The all sequences that are 1 over n to some number, those are sequences. Those will converge to 0, right, when we take the limit of those. So by the nth term test. So then we have to recognize, oh, this is a p series, all right? So then we kind of look and see what that number is to determine if it converges or diverges. So again, it converges when p is greater than 1. It diverges when p is between 0 and 1, including 1, all right? So if we look at these last 4 examples really quickly, all right, recognizing different types of p series, all right, if we're trying to determine if this series converges or diverges, I see 1 over n squared. This is a p series with p equaling 2, which is greater than 1, so therefore we converge. So this is all we would need to say. Example B. We have the series from 1 to infinity of 1 over the square root of n, also a p series where p is 1/2. That's between 0 and 1, so it diverges. Again, this is all we would need to say. Part C, we have a p series where p is 3/2, greater than 1, so it converges. Here, we have a p series where p is 1/3, therefore it diverges. Okay, so just recognize those different p series, identify your p value, and state converge or diverge. All right. One thing we need to make note of is it can be easy to confuse geometric series with p series. Remember, geometric series are where we have some number raised to the n power. So it's like p to the n power, or in this case, remember, it's a times r to the n. And that series would look something like this when we start writing those terms out. Geometric series converge when the absolute value of p is between 0 and 1, okay? And if we take a look, for example, if we have 3 times 1/5 to the n, all right, n is what's changing here. That power is what's changing. The base and that a value stays out front. Whereas a p series is 1 over n to some number. So we kind of switch the base and the power around. All right, so it's 1 over n to the p, where now the base of that denominator is changing. This converges when p is greater than 1 and diverges when p is between 0 and 1 inclusive. All right, if you have any questions on the integral test or p series, let me know.